All right. Good morning and welcome back. It's been a long time since we had a discussion, and today we are going to actually continue from where we actually left off. So I will do a small recap first to make sure that we are on the same page, literally. All right, and then we are going to actually start today's discussion. I hope that the audio quality is fine. Just please confirm if the audio quality is fine. Today we are going to talk about the one of the very important things here. I just hold on. This is not working. All right. So you might have forgotten what we last discussed, or you may remember what we last discussed. So we were actually discussing the stability of continuous time linear causal continuous time linear time invariant systems. Okay, and systems for which we can construct a transfer function. And that is something we were discussing. And then we actually proved that if we have a transfer function, and then if we can calculate the pole locations, then we can actually check out the pole locations, and if all of the poles have negative real parts, in other terms, if all of the poles resided on the negative half plane in sigma, essentially if all of the poles lied in the left half plane, so this half is known as the left half plane, okay, left of the imaginary axis, so this is the S plane, right? So this is the sigma axis and this is the omega axis. Sometimes just write j omega just to indicate that we are representing this with complex frequency terminology. If the poles are strictly there, then we say that the system is stable. All right. So this is well and good if we can actually calculate the pole locations. But sometimes what happens is that solving a polynomial to figure out the pole locations becomes very difficult. Okay. Solving a polynomial to find out the pole locations actually becomes very difficult. And under this scenario, we have to think about something important, is that in order to find out whether a system is stable or not, we don't need to exactly calculate the pole locations. We just need to know whether all of the poles lie in the left half plane or not. Okay. And if not, then how many poles actually lie in the right half plane? Doesn't matter really. If any of the poles lie in the right half plane, then the system is unstable. Okay, no matter what happens with the system. If any of the poles lie in the right half plane, then the system is unstable. So there is no question about that. But there is another form of stability which is called marginal stability, under which what happens is that a pair of poles possibly lies on the j omega axis, lies on this vertical axis. And under that scenario, if there are no poles in the right half plane, but there are some other poles in the left half plane maybe, okay, but if there are poles in the on the j omega axis, then what happens is that the system exhibits something that is between stability and instability. This is known as marginal stability. So the system responds with oscillatory response throughout its lifetime, and the oscillation never dies down. So the system doesn't ever reach a stable steady state, or it doesn't ever actually go to infinity and becomes shows instability. So it is like in between. Okay. So the thing is, Routh stability criteria, or in fact Routh Hurwitz stability criteria. So the thing is, there is something called Hurwitz stability criteria. Okay, Hurwitz stability criteria. Before we actually go further in this, let me just clarify a few terminology here. Okay, a few terminology. A polynomial, of course, the denominator is a polynomial, right? So just let me go back. So our transfer function, in our context at least, has a numerator polynomial and a denominator polynomial, right? So these are just two polynomials. So it's a ratio of two polynomials. Another polynomial. You understand what a polynomial is, right? So it's a combination of powers of integer powers of s, essentially. Okay. So the numerator is a polynomial and denominator is also a polynomial. All right. And It's a ratio of two polynomials. Okay. All right. And we said that, of course, the roots of the denominator polynomial are called the poles, and roots of the numerator polynomial are called the zeros, right? So the solutions, the roots of ds are called the poles of gs. Okay, because roots of ds are roots of ds are essentially those solutions. If you put them, the denominator becomes zero, right? These are called the roots of a equation of polynomial, roots of a polynomial essentially. So if you put the values here in place of d, in place of s here in this polynomial, what happens is that the denominator becomes zero. So gs actually kind of becomes infinity. So those are called the poles, and we actually discussed all this. And similarly, the roots of the numerator polynomial are called the zeros of gs, because obviously so for any value of s for which ns is 0, obviously gs will also be 0, right? So that with that understanding, we call that a zero of the polynomial, right? So we said that if all the poles, and in fact we proved, if all the poles are on the left half plane, then the system is stable, right? Then the system is stable. So that is something we actually proved in one of our earlier classes. Actually, I think it took 2 classes to arrive at that conclusion finally. Anyway, but now let me just write it down to be very specifically. So this polynomial ds, we are saying that the system is stable if ds has all the roots in the left half plane. So we are saying that gs is stable. I mean, gs is not stable exactly. When I say gs is stable, see, we are not talking about the stability of a transfer function. We are talking about the stability of the system that is represented with that transfer function. Okay. So when I say gs is stable, I actually mean that the system that is described by the transfer function gs is stable. Okay. Of course, not a transfer function cannot be stable or unstable, right? The system that is being described by the transfer function can be stable, can be unstable, can be something else. Right? So when I say gs is stable, it means the system described by the transfer function gs is stable. All right. So gs is stable if and only if. So this is how we write this: if and only if the poles, rather all the poles, poles of gs lies strictly on the left half plane, right? So if that is happening, then only the system is stable, we know. So we can actually rephrase this by saying, we can actually copy paste this and say, instead of saying all the poles of gs, we can say all the, we can simply say all the roots of ds, all the roots of the denominator polynomial. If all the roots of the denominator polynomial are on the left half plane, then the same thing actually happens, right? All right. So that is obviously we can actually say. So that is something we can say. All right. Now, if I have a polynomial and if all of its roots are on the left half plane, so the roots of the polynomial are all on the left half plane, then this polynomial is known with a special name. Okay. So a polynomial that has all of its roots on the left half plane. So if I have a polynomial that has all the roots in the left half plane, which means that all of its solutions, all of its roots essentially have negative real parts. Okay, left half plane, then the polynomial is called, it is called with a special name known as a Hurwitz polynomial, Hurwitz. Okay, so if all the roots are on the left half plane, then we call the polynomial to be a Hurwitz polynomial. So that's again, that's a terminology that you have to remember. All right. So here we can see that now with this terminology, we can say in order for this transfer function, or rather the system describing being described by this transfer function to be stable, the denominator roots, the roots of the denominator must be on the left half plane, or in other words, we can just say simply that this would be stable. This would be stable if and only if this is a Hurwitz polynomial. Okay, so only if this is a Hurwitz polynomial. Okay, one of you is saying that please repeat the GS for stability. Yeah, what we said that GS is stable, the transfer function is stable. Rather, the system that is being described by the transfer function is stable if all the poles of the transfer function are on the left half plane. So if all of them have negative real parts, right? This is something we derived throughout in our last two classes. All right, and then from that, of course, we can say that GS is stable if all the roots of DS are on the left half plane. That's obviously because the roots of DS are the poles, right? So if they are in the left half plane, then we say the system is stable. All right. All right. And now we just putting out a terminology out there that if I have a polynomial that has all of its roots on the left half plane, then we call the polynomial to be a Hurwitz polynomial. So it has a special name. It's called a Hurwitz polynomial if all of its roots are on the left half plane, right? So that is something we do say. So that's the terminology. So now we can say that if a transfer function is a ratio of two polynomials like that, okay, like a numerator polynomial divided by a denominator polynomial, just like what we have usually in our scenario. Okay, if we have something like that, then we can say that if ds, the denominator's polynomial, is a Hurwitz polynomial, which means if all of its roots are on the left half plane, which means if the system has poles that are entirely on the left half plane, right? Right? Then the system is stable. So a stable system indicates that DS will be a Hurwitz polynomial. Okay. So that is something you have to understand. Okay. Again, we haven't discussed anything very difficult here. I mean, what we are discussing here is something you probably know already. I mean, you're supposed to know already. All right. So again, if you still have any confusion, just make sure to ask. All right. Now the thing is, we could just calculate the roots of ds. We could just calculate the roots of ds. Oh yeah, we are going to talk about necessary and sufficient conditions shortly, so don't worry. Okay, yeah. When we say if and only if, it actually gives me a double-sided arrow. Okay. So when I say if and only if, it actually gives me a double-sided arrow indicating something like this. Okay. If and only if gives me a double-sided arrow. So this is what if and only if means. If and only if. So I'm saying that the system is stable if ds is Hurwitz. If and only if ds is Hurwitz, which gives me this bidirectional implication sign. Which means if the system is stable, then it definitely this is the Hurwitz polynomial. Also, if this is the Hurwitz polynomial, then the system is definitely stable. So it goes both way. All right. So that is if and only if. So when I say if and only if, that happens, right? And we are going to talk about what necessary and what sufficient condition really means shortly. All right. Just keep in mind that for the moment you can assume that something is written, and then if and only if something is written, then it means that there is a bidirectional implication symbol. Okay. So if this happens, then this definitely happens, and also if this happens, then this definitely happens. All right. So that is something you have to remember here, and we are going to explain this shortly. So now what Hurwitz figured out is that instead of calculating all of that, instead of calculating all the poles, because I mean all the roots of the denominator's polynomial, instead of doing all that, what if we can figure out a way in which We do not exactly find out the roots, but still can figure out whether a polynomial is a Hurwitz polynomial or not. Right? Hurwitz was the mathematician. Yeah, I'm going to explain if and only if, so please be patient here. All right. All right. So Hurwitz wanted to figure out a way in which you would be able to tell whether a polynomial is a Hurwitz polynomial or not. As a matter of fact, Hurwitz polynomial, so the name Hurwitz polynomial actually came from his work on polynomials, right? Obviously, because he figured out a way in which you can actually not solve for the roots of a polynomial and still figure out whether the roots of the polynomial are on the left half plane or not. Just hold on for a second. All right, sorry for the delay. So that is something we are discussing. We are discussing what Hurwitz did. So he actually figured out a way in which one can figure out whether a polynomial has all of its roots in the left half plane or not. So that is something Hurwitz figured out, and that's why the polynomial is known as a Hurwitz polynomial. Okay, because of his research work here. So he figured out a way in which you don't have to solve for the roots exactly. Okay, but you can still figure out whether the poles are on the left half. I mean, whether the roots of the polynomial are on the left half plane. And this work was later extended by Routh, Edward Routh, and he actually invented a way in which you can actually simplify the procedure. So Hurwitz defined a procedure in which you can actually do some operation on a polynomial, okay, using the coefficients of the polynomial, and you can figure out whether the roots of the polynomial are on the left half plane or not. Okay, and then Routh actually figured out a way in which you can do that in a much simpler fashion. And in fact, Routh used, this entire theory is built upon certain very complicated theories in complex analysis, algebra, okay, things like something called strum chains. Okay, so you just might need to remember these names, but I cannot explain these things because unfortunately the mathematical rigor in the background of the proof of this is a bit too high for any undergrad engineering students. Okay, so the things that we need is strum chains. Actually, in order to prove what we are actually trying to say momentarily, okay, strum chains, then we need something called Cauchy's principle of argument, rather. Okay, and a few more things, divisibility. These are parts of these are different parts of different domains of mathematics. Okay, you do not really discuss these things in a single subject. Okay, and of course there is a research paper which was published by Routh which went through all of that to actually arrive at the conclusion that we actually use regularly. So this is one of those things that I, even if I wanted to, cannot actually show you how it actually works, rather why it works. Okay, I can show you how it works, I cannot show you why it works. Okay, because I cannot actually prove it to you. Okay, this is a very complicated proof, to be very frank here. Okay, but the ultimate result, the final result that we obtain out of this is a very simple and intuitive and useful thing. Okay, very simple and intuitive and useful thing. So what we are going to do instead, we are going to actually leave this here, and we are going to develop what we are going to actually talk about what that Routh-Hurwitz stability criteria is. So our intention, or rather our goal here, as I already mentioned, is that we want to figure out whether a polynomial is Hurwitz or not. Especially, we want to figure out whether the denominator's polynomial for a transfer function is Hurwitz or not. Rather, in other words, what we want to figure out is whether all the poles are on the left half plane or not. All right. And out of that, we are trying to figure out whether the system is stable or not. So that is something we are discussing here. All right. So Routh-Hurwitz, so he actually tried to simplify the process and figure out a way in which you can, rather, I should say, in a rather simple fashion, you can figure out whether the system is stable or not. Okay. So instability kind of has a very simple criteria. You see. Okay. So this criteria, we are not saying criterion. Okay, we are saying criteria. Criteria is a plural of criterion. Okay, so there are more than one things to discuss here. Okay, so there is one necessary criteria, there is one sufficient criteria, and I'm going to explain the term necessary and sufficient very clearly here. Okay, I did discuss that using a class in one of our earlier classes, but here I'm going to explain this in a bit rigorous fashion. Okay, necessary criteria. So what do I mean? The condition that I'm going to put together right now is necessary for a polynomial to be Hurwitz, but it is not sufficient. Okay. In order for a polynomial to be Hurwitz, this is necessary, but this is not sufficient. Okay. So let me just write it down. So how do I place this? All the all of the coefficients of a polynomial should have the same sign and none of them can be 0. Okay, so this is the necessary condition for a polynomial to be a Hurwitz polynomial. Okay, rather we say that for a polynomial to be a Hurwitz polynomial, okay, rather let me just bring this. For a polynomial to be a Hurwitz polynomial, right, all of the coefficients of the polynomial should have the same sign and none of them can be 0. So that is the necessary criteria, and I'm going to explain these things a bit rigorous way. Okay, so you have to now figure out what is the implication of what is the condition here. Okay, right? And if I ask you, okay, what is the implication, what we are trying to figure out? Now, of course, we are trying to figure out this. Okay, we are trying to figure out this. Okay, and That is the implication here, or that is the outcome that we are looking for. Okay, and the condition is this. Okay, so that's the condition. So this is the outcome, the other implication, what we wanted to figure out, whether the polynomial is a Hurwitz polynomial or not. Of course, you know what Hurwitz polynomial is. So this is what we want. This is the implication, and this is the condition. Okay. All right, and I'm going to explain what it means to be a necessary condition. Necessary condition. All right. So let me give you a few examples, and it will be very clear with the examples. Okay. So let's take a polynomial. Okay. So question is, is this polynomial is the Hurwitz polynomial? So for example, this appeared in the denominator of a transfer function. Okay, if this appeared in the denominator of a transfer function, so would we say the system is stable or not? In other words, whether or not we are trying to figure out whether or not this is a Hurwitz polynomial. But in other words, we are trying to figure out whether or not it has all of its solutions, all of its roots in the left half plane. Now question is, what are the coefficients here? What we have to figure out here is that what are the coefficients here? So one of the coefficients is 2, and one of the coefficients is 7, and there is a coefficient which is -3, and that is violating the necessary criteria. Okay, so it is violating the necessary criteria. Then what we're saying is that now we see that the coefficient of s to the power 1, so it is like s to the power 1, and this is of course s to the power 0. Okay, the coefficient of s to the power 1 does not have the same sign as the coefficients of the other things. So for example, what we mean is that all the coefficients should have the same sign. Either all of them are positive or all of them are negative, and none of them can be 0. Okay, none of them can be 0. So we can see that one of the coefficients is negative. One of the coefficients is negative, and thus we can definitely say it does not satisfy the necessary criteria for stability. Okay. All right. So rather must have. Here instead of should have, I should say must have. All right. So it is not a Hurwitz polynomial, right? So just hold on. I'm going to cut these through and write it in a more rigorous mathematical way. Okay. So don't write it down in case you are writing it down, but of course the handouts will be available on this. Okay. So what is it? So this is not a Hurwitz polynomial, right? So we can say not Hurwitz. The conclusion is it is not Hurwitz. Okay, it is not a Hurwitz polynomial because it is violating the very necessary criteria, right? All right. So let me give you another example, maybe. All right. Now, is it a Hurwitz polynomial or not? The answer is no, it is not a Hurwitz polynomial. Why? Why is it so? Because it is missing one of the coefficients, which means that the coefficient of s to the power 1 here, the coefficient of that is actually 0. Okay. So this is just like 5s cube plus 7s square plus 0s plus 9. So that's how it is not a Hurwitz polynomial, right? Not a Hurwitz polynomial. All right, and let me give you another example. Now, is it a Hurwitz polynomial or not? The answer is we don't know. We don't know. Because the problem is the necessary criteria tells me what is necessary to be Hurwitz. Okay. So if it violates the necessary criteria, then it is definitely not Hurwitz. But if the necessary criteria is satisfied, then we don't really know whether it is Hurwitz or not. It could be Hurwitz, it could be not. Okay. But if it violates the necessary criteria, then what happens? Then we definitely know that it is not a Hurwitz polynomial. Okay. So for a necessary criteria, instead of writing it that way, we should say it's the other way around. We should say that if the implication is false, so this is how we write it. If the implication is false, rather, so if the condition is false, that implies that the implication is definitely false. Okay, so that's the mathematical notation. If the condition is false, then the implication is definitely false. So that is how we write down necessary criteria. Okay, so instead of writing it this way, just hold on. All right, so that is what necessary conditions are, right? So if so necessary condition for Routh Hurwitz criteria here in order for a Hurwitz, so if the condition is dissatisfied, then it is definitely not Hurwitz. If the condition is satisfied, we have to check further. We have to check further and figure out whether the system is stable or not. Okay, we have to figure out whether the polynomial is actually Hurwitz or not. Okay, but if the necessary criteria is dissatisfied somehow, we definitely know it is not a Hurwitz polynomial. So in view of that, we can actually modify our statement to be slightly more mathematically correct, in my opinion. Okay, so what we can do, instead of saying this, we can rephrase this statement, and that actually becomes better. Okay, we would say if a polynomial does not have the same sign for all of its coefficients, or if any of the coefficient is 0, which means the term is missing, that is the corresponding term is missing. Then the polynomial is definitely not a Hurwitz polynomial. Okay, so that is a good statement to make when we are actually writing down any necessary conditions. So in my opinion, you would you would find this kind of statement in pretty much all the books. Okay, but this is not how you write necessary conditions. So necessary conditions, so here of course you understood that here it says that if the condition is not satisfied, that implies that the implication will not be satisfied, but it is not the other way around, right? So that is how it is a necessary condition for this. So if that is dissatisfied, then that is going to be dissatisfied as well. All right, but here we are writing it in a proper fashion, exactly what we have written mathematically speaking. Okay, so that is how necessary conditions are. Okay, what we are saying is that here we are going to say the polynomial does not have the same, if a polynomial does not have the same sign for all of its coefficients, or if any of the coefficients is 0, that is the corresponding term is missing, then we say that the polynomial is definitely not a Hurwitz polynomial. If it is other way around, then we say, then yes, it may be Hurwitz, maybe not. But this is how we write necessary conditions. So in my opinion, this is a better way of writing this. This is a much better way of writing this. All right. So you already understand the necessary criteria there, right? So if the necessary criteria is not satisfied, then it is not Hurwitz. Your work is over. You know you are dealing with an unstable system, right? Then you need the sufficient criteria. If we have a polynomial that satisfies the necessary condition, then we say, okay, it is not. We are not sure exactly whether or not it is Hurwitz really, but it is not directly ruled out. It is not immediately ruled out. For example, this one, it is not immediately ruled out whether or not this one is a Hurwitz polynomial, right? So if we are there, then we have to construct something called the Routh table. Okay, Routh table, and check for something else as the sufficient condition. Now, again, we are going to explain what a sufficient condition really means, but okay, we're saying this. Just hold on. Sufficient condition. So this is sufficient condition, and again, sufficient conditions are those kind of conditions. If this is satisfied, then it is definitely a Hurwitz polynomial. Okay, just let me write it down. Sufficient condition. So if we're saying a polynomial, let me just rephrase this up here. Let me just write down a polynomial let me just write down maybe a Hurwitz polynomial if all of the coefficients of the polynomial just has, let's just say, have, yeah, better way of writing this. All right, but this is a much better way of writing this. I hope you understand what I'm saying here. Again, if you have any confusion, feel free to ask. A polynomial, we are saying a polynomial is definitely a Hurwitz polynomial if the first column of the Routh table, and what is the Routh table? I'm going to explain. A polynomial is definitely stable, definitely a Hurwitz polynomial if the first column of the Routh table for the polynomial rather just if all the elements in the if all the elements in the first column of the Routh table for the polynomial have the same sign and none of them are 0. So now again, just try to figure out what is the implication here. The implication is a Hurwitz polynomial. A polynomial is a Hurwitz polynomial, right? So that's the implication once again here. And what is the condition? Condition is that if all the elements in the first column of the Routh table for the polynomial have the same sign and none of them are 0. That's a condition here. Okay. So this is the implication here. And this is the condition. And since it's a sufficient condition, what we are saying is that the condition in fact implies the implication. So if the condition is satisfied, then it is definitely a Hurwitz polynomial. Okay. Now how to construct a Routh table. Okay, that is a very important thing here. How to construct a Routh table. So let's say we have a polynomial. So let's say just we have an arbitrary order polynomial. Let's just say we have a polynomial that looks like just one. All right, so let's say we have a polynomial of any arbitrary order, say order n, okay? And of course, we are dealing with the denominator's polynomial for transfer functions, right? So let's just write it down. Say we have a polynomial that looks like this. A n is to the power n plus a n minus 1 is to the power n minus 1 plus a n minus 2 is to the power n minus 2 plus a n minus 3 is to the power n minus 3 and so on. So it's an nth order polynomial. It's a very standard way of writing an nth order polynomial, right? So now we are checking whether this polynomial is a Hurwitz polynomial or not. So first thing we need to do, we need to check for the necessary condition. We need to check for the necessary condition, and we have to check. So the necessary condition, what we have to check, if the necessary condition is violated, then we know it is not a Hurwitz polynomial. So we have to check whether all of that, a n minus 1, a n minus 2, up to a1, a0, all the coefficients, okay, have the same sign. Okay, should either all be positive or should all be negative. Okay, or should all be negative. So all the coefficients must all be positive or must all be negative. Okay, there cannot be any changes in the sign. If that is, if this condition is violated, then it is absolutely done. So we definitely know that the system is not stable. Okay, then we definitely know the system is not stable. If any one of them is 0, then obviously this condition is dissatisfied, is that one of them is equal to 0, not greater than, neither less than. Okay, so that's a necessary condition. For the sufficient condition, we have to construct the Routh table. And for checking the sufficient condition, we have to construct the Routh table. So this is how we construct the Routh table. Okay, so let me just write it down. So we construct the Routh table like this. So we say s to the power n and s to the power. So this is a table, just like any table. Maybe I won't put these lines here because that way it becomes very difficult to see. So this is the next row. This is the row after that. This is another row. This is another row, and so on and so forth. These rows keep on going. Okay. Now, again, this is quite unfortunate, is that the fact that I cannot actually prove this in front of you, because the mathematical background that is required to prove this kind of thing is beyond our capability, at least for this class. So we cannot prove this. Otherwise, I would have shown you why this thing is the way it is. Okay, all right. So what we're trying to write down here, we are going to write down the coefficients here. So again, so Routh and Routh actually made up a way in which you can construct a very simple table, and then out of that very simple table, you can tell whether the poles are on the left half plane or not, whether the polynomial is a Hurwitz polynomial or not. Okay. So what we can do, we can actually bring out these coefficients here, but one after another, like with a gap of 1. So the first one would be an. The next one we were going to write is going to be an minus 2. The next one is going to be an minus 4, and so on and so forth. Okay. So this is how you write it. Please don't ask me why we write it this way, because we are not going to prove it here. Okay, and here we write a n minus 1, here we write a n minus 3, here we write a n minus 5, and so on. All right, the next thing that is going to appear here is going to be this determinant. So it is going to be a determinant with a negative sign. Okay, it is going to be the determinant of this with a negative sign. Okay, with a negative sign put outwards. Okay, so you are going to multiply these two, subtract these two, subtract the product of these two, and put a minus sign outside. But instead of saying that, what we say, we multiply these two first, and then we subtract these two. So remember this symbol here. So this is how we actually write this out. The same thing as having a determinant and putting a minus sign. Okay, it is the same thing as multiplying these two first and subtracting the product of these two. Okay, so the next term here is going to be a n minus 1 a n minus 2 minus a n times a n minus 3 divided by this term. This term is called a pivot term. Okay, divided by this a n minus 1. All right, so that is something which is going to be the first term here. Let me just write it in a better way. So this is going to be a n minus 1 times a n minus 2 minus a n times a n minus 3 divided by a n minus 1. Hold on. All right, that's the first term. Okay, first term in the next one. So we actually construct the first two rows using the coefficients of the polynomial, and then we construct the next rows using this terminology. So this is the pivot term here. Okay, and then the next one would be like this. We start from here, we take the determinant of this and this, okay, and put a negative sign, which means we can actually do this calculation in a very simple fashion if we remember this. So remember this structure here. Okay, that's very similar structure. Right, so what we're doing, we are starting from here once again, multiplying these two, and then subtracting the product of these two. Right? Right? So this is still the pivot term. So the next term that we're going to write here is going to be a n minus 1 times a n minus 4 minus a n times a n minus 5 divided by a n minus 1. That's going to be the next term. And this file is once again going to be available with you, so you can actually zoom it in however you want, however much you want. Okay, all right, and obviously the next term here will be corresponding to this multiplied with whatever stands here. Okay, subtracted and then subtract what this multiplied with whatever is standing here divided by this, and so on and so forth. So this is going to be continued there. Okay, now what about, so let's call this thing, this entire thing to be something like b1. Okay, let's call this entire thing to be something like b1. Okay, and if I call this thing to be B1, and let's call, sorry, not B1, let's just call it Bn. Oh, yeah, Bn, that's fine. And let's call this Bn minus 1. Okay, whatever. And then the next term, for the next term, this would be considered to be the pivot. This would be considered to be the pivot. Okay. Now, obviously, the next term correspondingly would be Bn times An minus 3 minus An minus 1 minus Bn minus 1, sorry, times Bn minus 1 divided by Bn. Okay, so because that is the pivot term here. All right, and subsequently whatever term appears here, so this multiplied with this, and then subtract this multiplied with whatever appears here. All right, I put it there. If there is nothing, okay, if there is nothing, assume that to be a 0, and so on and so forth. We construct this table accordingly. Okay, this is how we construct this table. I'm going to show you examples. But what this sufficient condition told us is that this is the first column of the Routh table. You notice very carefully. So this is a table, and this is the first column of the table. So this is the first column of the table. What we are saying is that a polynomial is definitely a Hurwitz polynomial if all the elements in the first column of the Routh table have the same sign. If all the columns, if all the elements in the first column of the Routh table have the same sign. Okay, that is something we are saying here. All right, so let's see a few examples and then figure out how that actually really works. Okay, so I have curated a few examples, and those examples will be better for you to actually see, because in my opinion, you need to see a few curated examples first. Okay, curated means specially collected examples. Okay, and that will actually help you in understanding what we are saying here. And again, I have given you a set of exercises, and there you already have these curated questions here. Okay, let me just switch to this view. All right, so this is a set of curated questions that we have, for example. All right, so let's see a few one of these. All right, so let's check this one. That's going to be x to the power 4 plus 2s squared 2s cubed. Okay, so this is the denominator of a transfer function. I do not know what is there in the numerator. That doesn't matter. Okay, so this is the denominator. This is in the denominator of a transfer function, and we are trying to figure out whether the system is stable or not. Okay, so first you need to do the check for the necessary condition. All right, so you have to check the necessary condition. All right, so first we have two check boxes. One is for necessary condition, one is for sufficient condition. And unless the checkbox for the necessary condition is satisfied, we do not go to the sufficient condition checking. Okay, so this is the necessary condition. Okay, and this is the sufficient condition checking. All right, so in order for it to satisfy the necessary condition, all the coefficients must be present. So there should not be any particular power missing here. So we have power 4, it's a fourth order polynomial. Then we have power 3, 2, 1, 0. So the example that I just took satisfies the sufficient condition, and that's why I actually taken this particular example. Okay. All right, so you can see that all of the coefficients here, of course the coefficient is 1, all of the coefficients are present and none of them are missing. So all of them have the same sign. Okay, and none of them are missing, so it is satisfying the necessary condition, which means this could be stable, this could be unstable. I'm not really sure, but I'm not saying that this is definitely unstable. So it satisfies the necessary condition, so that is satisfied. Okay. Now I have to check for the sufficient condition, right? So I'm not ruling it out as an unstable system. right away. Okay, because it satisfies the necessary condition. If it dissatisfied the necessary condition, then I would just straight away tell you that this is an unstable system. End for the story. End of the story, right? But since it satisfies the necessary condition, I have to now go forward and check, construct the Routh table, and out of that we have to check whether the system is stable based on the sufficient condition. And if the sufficient condition is satisfied, then we definitely say it is a Hurwitz polynomial. So the system is stable, in other words. Okay, so let's construct the Routh table. So we are checking the sufficient condition. And to check that, we are going to construct the Routh table. Okay, and if we construct the Routh table, so let's say we have, of course, s to the power n, so that's going to be s to the power 4. Then we have s cube. Then we have s square. You know what? I am going to pull it up a bit. All right, so Routh table, let's construct the Routh table. So this is going to be s to the power 4. So this is just a name for the rows. Okay, s cube row, s square row, s to the power 1 row, and then we have s to the power 0 row. Now we have a complete set of rows that I can actually show you at least. So this is once again a table. Okay, so these are the rows correspondingly, and I have to put elements in the columns as well. Okay, and then we have these columns. But for the sake of simplicity, we do not draw it as a table. Okay. So, right, for the sake of simplicity, we do not construct it as a table like this. I mean, if we do, I mean, if we write down all these, I mean, it becomes really difficult for actually to write anything down. For this example, I'm going to do this way. Okay, but we skip these lines here. Okay, skip these borders here. All right, so now the polynomial has these coefficients 1, 2, 10, 8, and 3. Okay, so what we do, we skip one power each, right? So here when we write it, so this is going to be 1, this is going to be 10, and this is going to be 3. All right, and for the next one, we are going to write this one and this one. Sorry, I mean this one, right? So this is going to be 2, 8, and nothing, so 0. All right, so that is something we have here. All right, we can skip writing this. That's also a fine alternative here. If there is nothing, I mean, we just assume it to be 0. Okay, so better to write 0 here than actually skipping it, but you can actually skip it, not a problem. All right, so that's the first 2 rows of the corresponding Routh table. Okay, so now what you need to do, you need to consider this to be the pivot term and calculate this determinant with a minus sign outside. Okay, and write down as the next term, and of course divide it by 2. So what we are doing, we are taking that as a pivot term, we are doing this multiplication, so we are multiplying this with this and subtracting the product of these two and dividing it by 2. So in other words, you know how that works. It becomes 2 times 10 minus 8 times 1, rather 2 times 10 minus 1 times 8 divided by 2. Okay. 2 times 10 minus 1 times 8 divided by 2. So 2 times 10 minus 1 times 8 divided by 2. And how much is that? I have 20 minus 8, so that's going to be 12. Right, obviously the answer is 6, right? The answer is 6, so let's write it down. The answer is 6. Okay. Obviously for the next one, what we are calculating is that we are taking this. Obviously we are taking this, multiplying with this, subtracting the product of these two. And obviously here I don't have anything, so I have 0. It is assumed like that. So this is going to be 2 times 3 minus 1 times 0. Okay. Here, if there is nothing, we assumed it to be 0. Okay. And obviously divided by 2, because 2 is the pivot term here. Okay. 2 is the pivot term here. And obviously the calculation ultimately gives you 3, right? That's the 3. And thus we have constructed the new row. Okay. New row of the Routh table. And obviously if there is nothing here, assume it to be 0, but we can actually skip that, right? Okay. So you know how that actually works. Okay. What about the next one now? Okay, for the next one, this is the pivot term. For the next one, this is the pivot term, and correspondingly, you have to do this calculation. Okay, take this, and this. So you have to take this, multiply with this, and subtract the product of these and this. So this is going to be 6 times 8 minus 2 times 3 divided by 6, whatever that is. Okay, that's going to be 6 times 8 minus 2 times 3 divided by 6. 48 minus 6, that's going to be 42. Okay, that's going to be 7, right? Okay, and this calculation ultimately yields 7. Okay, so this is the 7. And obviously there is no other calculation required, because if I had assumed a 0 here, then obviously the calculation would be 6 times 0 minus 2 times 0 divided by 6, and that would be 0. But that is unnecessary. Okay, so we don't put that here. Okay, so we have that. And again, we can assume a 0 here. And now we have this pivot term here. We can assume a 0 here. And now this is the pivot term, and obviously we calculate this product and subtract this product, right? And divide by 7, obviously. So obviously we have 21 minus 0 divided by 7, and that gives you 3, right? Let me just write it down once again. So that's going to be 7 times 3 minus 6 times 0 by 7, and that obviously is 3. All right. So we have now constructed the full Routh table for that polynomial we had. Okay. For this denominator polynomial, we have constructed the Routh table. And in the Routh table, now look very carefully at the first column of the Routh table. So this is the first column of the Routh table, right? This is the first column of the Routh table, right? And look very carefully at the first column of the Routh table. The numbers that you see, this 1, 2, 6, 7, and 3, all of them have the same sign and none of them are 0. All of them have the same sign and none of them are 0. That indicates that it satisfies the sufficient condition, and as such, this polynomial is corresponding to a stable, or rather a Hurwitz polynomial. And since this polynomial is the denominator's polynomial, we say all the roots of these polynomials are on the polynomial are on the left half plane, which means the system is stable. All right. So that is something we want to discuss here. So we are saying that yes, it does satisfy the sufficient condition. So it does satisfy the sufficient condition, and as such, the system is actually a stable one. Okay. All right. So we say all the elements in the first column of the Routh table let's just say positive, or say have the same sign, and none of them are 0. So it satisfies the sufficient condition. So the polynomial is Hurwitz polynomial. So this is the Hurwitz polynomial. So we say that this is the Hurwitz polynomial. Therefore, this is the polynomial here. The system is stable. So that's our final conclusion, right? Wow. Okay. So because we know that this condition is satisfied. So I think it is understood, I hope. All right. So now let's see another example. Okay. As I said, I have curated a few nice examples. All right. Okay. So let's say this is the polynomial. And of course, this is probably in the denominator of a transfer function, and that is something our discussion revolves around, right? So this is the polynomial we are dealing with, and we are trying to figure out whether the system is stable or not. So we are trying to check whether this polynomial is a Hurwitz polynomial or not, right? So let's construct the Routh table as usual. Okay. Not a problem. Okay, you know what? Let's construct a very complicated one, maybe. Okay, let's construct a big complicated one. All right. Let's just say, well, I'm going out of the, what should I say, standard well curated problems here. Okay, let's construct a big one. And you know what? I'm not All right, you know what? Let's keep it the way it is. All right, so that is the polynomial because I want to complete this class in a single go here. All right, so here let's say we have to construct the Routh table corresponding, right? Because we know it also satisfies the necessary condition, so not a problem there. I'm not sure about the sufficient condition, but let's say it satisfies the necessary condition, so that is fine with us. So let's construct the Routh table. So it's going to be s to the power 4 s cube okay. So we are checking for the checking whether the sufficient condition is satisfied or not. All right. So we have to once again take the coefficients out. This is 1, obviously. And then we have 4, 8. Nothing we can actually just, next one is nothing, so we can actually skip it. Now there is one important thing you need to note here. Okay. So when you are constructing the Routh table, what you are actually checking, figuring out. So again, I told you that some sort of divisibility criteria is there built in. Okay, some sort of divisibility criteria. Okay, some sort of factorization theorem is associated with this. Okay, and as such, whenever you have numbers like these, you can reduce them as much as you want by taking out positive factors. Okay, so you can actually take out positive factors, keep in mind. Okay, so there is one thing you need to note. Instead of writing 4 and 8, you can take out positive factors. But this is completely optional. Okay, this is completely optional. If you don't do this, you are going to still end up with the correct result. So here we have 4 and 8. I can just keep it as it is or as they are. I can keep them 4 and 8 without any hesitation, and result will be exactly the same. The inference we draw would be exactly the same. There won't be any change whatsoever. Okay, but our calculation will be slightly simpler. So what we do, instead of writing 4 and 8, we would actually simplify them by taking out a positive factor. So that's the important thing here. Take out positive factor. Okay, we cannot take out negative factor. Okay, you can take out positive factor. So here, what is the largest positive factor I can take out? Of course, that's gonna be 4, right? And why take out positive factors? Because if we take out negative factors out, so then what happens is that it changes the sign, right? I don't want that. So this becomes 1 and this becomes 2. So right off the bat, we actually modify the Routh table. So instead of writing 4 and 8, so there was supposed to be 4 and 8. Instead of that, we actually write 1 and 2. Okay, we actually don't write that 4 and 8. Okay, so that's our new part of the Routh table here. All right, and let's try to do the same calculation once again. So again, since there is nothing here, we put a 0. We imagine a 0 here. Okay, and this is the pivot term here. And we calculate this product, subtract this product, and divide it by this value. Okay, so here it is going to be 1 times 1 minus 1 times 2 divided by 1. That's going to be minus 1, right? So this is going to be minus 1. All right, and that is going to be minus 1. So let me just make this very small. This calculation, that actually gives me a minus 1 here. That is actually minus 1. Similarly, multiply these two, subtract the product of these two, divide by this, and that way you get something like 1 times 1 minus 1 times 0 divided by 1, and that is actually 1, right? So that is actually plus 1. Okay, that is actually plus 1. All right. Now what about the next one? Now this is your pivot term. Okay, this is your pivot term, and yeah, you are right. So subsequent terms are just as fine, right? Not a problem. So take this, multiply these two, subtract the product of these two, divide by this, and so that becomes minus 1. That becomes minus 1 times 2 minus 1 times 1 divided by minus 1. Okay, so that's gonna be minus 2 minus 1, that's gonna be minus 3 divided by minus 1, that's gonna be 3. So now we once again have a positive term. So we now once again have a positive term. That's gonna be 3. All right, and nothing here because of course we have 0 here. If you imagine, we have 0 here, so product is 0, divided by minus 1, so 0. No need to write those. Okay, you could imagine a 0 here because that is what we got. You can actually skip writing that, not a problem, right? And then of course the next term would be 3 times 1 minus minus 1 times 0 divided by 3. So let's write it down. That's going to be 3 times 1 minus minus 1 times 0 divided by 3, and that's obviously 1. That's obviously 1, and that's obviously 0 here. I don't care. All right, so that is something you have to write down here. So that is the end of the Routh table. Now you see, looking at the first column of the Routh table, you see that not all of them have the same sign, right? So we have a positive, then we have a negative one, then we have a positive. So there is a change of sign here, so it does not satisfy the sufficient condition, so the system is unstable, which means this polynomial is not a Hurwitz polynomial. This is not a Hurwitz polynomial. Okay, this is not a Hurwitz polynomial. So there are poles of this, roots of this that are on the right half plane. So this system would have poles that are on the right half plane. Okay, this system would have poles that are on the right half plane because this polynomial has roots that are on the right half plane. So the system is unstable. Okay, now the funny thing is that, or rather the nice thing is, this does not only tell us whether or not the system is unstable, it in fact also tells us how many poles would be on the right half plane, how many roots of the denominator polynomial would be on the right half plane. Not only that, okay, this is stable, this is unstable, not only that binary answer, okay, but also it tells us how many of them are on the right half plane. Okay, so let me just write it down. When we construct the sufficient condition table or the Routh table, we say, very importantly, wow, it is not even in boring. Let's just say the number of sign changes in the first column equals number of roots in the right hand plane. So now this sufficient condition table or the Routh table does not only tell us about the system being unstable. Okay, it tells us that, okay, this is not a Hurwitz polynomial, so it does not satisfy the sufficient condition, so end of story. But what it tells you is that along with that, it tells you how many poles are on the right hand plane. How many poles are on the right hand plane? This is exactly what it tells you. So in other words, we can say that, see, let's see how many sign changes there are. Okay, how many sign changes there are. So this was positive, and from positive we are going to a positive quantity, right? In the first column, if you look through this, so from positive to positive, how many sign changes? 0 sign changes. But now we have from positive to a negative quantity. How many sign changes? 1 sign change in total. Now then we also have from negative to a positive quantity, right? So that's another sign change. That is counted as another sign change. And for the last one, this is not a sign change because it's from a positive quantity to a positive quantity. So we have 2 sign changes in total. Okay, here is 1 sign change from a positive quantity to a negative quantity. Then there is another sign change from a negative quantity to a positive quantity. So there are 2 sign changes here. Okay, so there are 2 sign changes. Okay, so these 2 are the 2 sign changes. Two sign changes, and that's how we can say that not only this polynomial is not a Hurwitz polynomial, but we also know some specific details about this polynomial. Okay, so what we can say that this system is not only unstable, but there are 2 poles that are on the right half plane. So 2 sign changes would actually indicate that therefore there are 2 poles of the system in the right half plane. There are 2 poles of the system in the right half plane. Okay, so that is something we can actually establish out of this, and of course the rest would be on the left half plane, obviously. So there are 4 poles, and obviously the rest 2 are on the left half plane, obviously. So but what we can conclude out of this is that therefore the given system is unstable because it has 2 poles on the right half plane, and the remaining 4 minus 2, so of course 4 was the order of the polynomial, so there are 4 poles, obviously. 4 minus 2, which is equal to 2 poles, are on the left half plane. Obviously, since there is at least 1 pole in the right half plane, the system is unstable. Okay, so what we are seeing is that without actually finding out the exact locations of the poles or poles here, without actually solving this polynomial, without actually calculating the solution, without actually figuring out the roots, okay, without actually figuring out the exact pole locations, we can tell how many of the poles are on the left half plane, how many of the poles are on the right half plane. All right, that's very important for us. And not only that, later on in the next class we are going to see how we can also figure out how many poles are on the j omega axis also. Okay, so it can actually give you all these ideas comprehensively. Okay, so let's end with one big example. Okay, one big example, and that would be, I think, the end problem here. Okay, let's take another example. Let's say another system is there, and this is the numerator. Okay, and say it's a 7th order polynomial. Okay, so s to the power 7, let's say 2s to the power 7 minus, so plus let's keep these small numbers, okay, because otherwise the calculation would be pretty bad for me, at least. So all right, so it's a 7th order polynomial. I mean, solving this manually becomes really difficult, right? Really difficult. And we can see right off the bat that it satisfies the necessary condition, because all the coefficients are present here. None of the coefficients are missing. S to the power 0, 1, 2, 3, 4, 5, 6, 7. All the coefficients are present there. None of them are missing. And so it satisfies the necessary condition. Not a problem. Okay. So now it's a candidate that we need to check using the sufficient condition. I don't really know whether it satisfies the sufficient condition. So let's check that. Okay. All right, so we have to construct the Routh table. Now this Routh table is going to be a gigantic one. Okay, so this is going to be s to the power 7. This is going to be s to the power 6. Let's just write it up to this one. Okay, so the coefficients that we have to pull together are 2. Just write 2, and that's going to be 3, 2. So 2, 3, 2, 3, 1. Right, it's a very big one. And for the next ones, it's going to be 5, 3, sorry, I mean 5, 2, what am I doing? It's going to be, oh, sorry, what did I do? I made a mistake. Extremely sorry, just hold on. This is going to be 2, 3, 1, 4. Yeah, 2, 3, 1, 4, I mean. 2, 3, 1, 4, right? And for the other one, it's going to be 5, 2, 3, 1. It's going to be 5, 2, 3, 1, right? So those are the coefficients that we actually write down. Okay. There is nothing here, so which means it is 1. All right, so that is the end of this. All right, so we have constructed the first two columns, at least first two rows. Okay, so now we have to construct the next one. So that's going to be s to the power 5. Okay, so this is going to be the 15 minus 4 divided by 5. How much is that? So I have to bring out a calculator. So hold on. And it's going to be a very simple algebraic calculations nonetheless. So basic mode is just fine for this. Okay, so it's a basic calculator. I'm just keeping it here. All right, and so we have 15 minus 4. So that's going to be 11 divided by 5. So 11 divided by 5. That's going to be 2.2 here. It's going to be 2.2. So this minus this divided by this. Okay, so that's going to be 2.2. Now this minus this divided by this. That's going to be 5 minus 6 divided by, that's going to be 5 minus 6 divided by 5. Okay, so that's going to be minus 1 divided by 5. That's going to be minus 0.2. Okay, that's going to be minus 0.2. And this times this, that's 20 minus 2 divided by 5. All right, so that's the pivot term once again. That's 20 minus 2 divided by 5. That's going to be 18 divided by 5. 18 divided by 5. That's going to be 3.6. And there is nothing to worry because here we have 0. Yeah, so forget that. That's the end of this next one. All right, nice. So now s to the power 4 row. So this is now my pivot term. This is my pivot term. So this times this minus this times this divided by this. So now this is going to be a very complicated calculation in my opinion. Let me just do this. So that's going to be 2.2 times 2. Okay, minus. So that becomes a plus. So plus 1. Yeah. So that's going to be 5.4. Okay. That's going to be 4.4. And so 5.4. And now divided by 2.2. That gives me 2.45. That becomes 2.45. that becomes 2.45. All right. Now we have to multiply these two, subtract these two, divide by these once again. So 2.2 times 3, that's going to be 6.6 minus 5 times 3.6. All right. So that's going to be 2.2 times 3 minus 5 times 3.6, and let's divide that by 2.2. So that's divided by 2.2. That's going to be minus 5.18. That's going to be minus 5.18. All right. Now obviously this multiplied by this, sorry, I'm really sorry. This multiplied by this and subtracted from this product, and obviously there is nothing here, which means there is a 0 here. Okay, so that's going to be 5 times 0. So what we are saying here is that that's going to be just 1. Okay, 2.2 times 1, that's 2.2 minus 0 divided by 2.2, so that gives me 1. So now s cube, so this multiplied by this, so this is the pivot term here. Okay, this is the pivot term. So this multiplied by this, subtracted from this product, and then divided by this. So now let's see. We have minus 0.2 times 2.45. Sorry, 2.45. 2.45. Please keep up with the calculation, maybe. And that plus is 2.2. 0.2 times 2.45 minus, so becomes plus 2.2 times 5.18, whatever that is, and divided by 2.45. Okay, so that's 4.45. That's 4.45. All right, and same thing here, multiply these two, subtract the product of these two, divide by this. So here we have 3.6 times 2.45 minus 2.2, and let's divide that by 2.45. That's going to be 2.7. That's 2.7. Yeah. Okay, nice. So thank you, those who are actually following along properly. Thank you very much, really. Okay, and product of these two, subtracted from the product of these two, divided by this one. All right, so again we can assume a certain 0 here. Okay, so now this becomes 4.45 times, sorry, with a minus sign, right? Minus 4.45 times 5.18 minus 2.45 times 2.7. Okay, and divide that by 4.45. So yeah, that's going to be minus 6.67. Minus 6.67. And for this one, of course, that's going to be 1. This times this minus this times this, divide by this. That actually gives you 1. All right. So now let's write s to the power 1. This times this minus this times this, divided by this. Okay. So once again, help of calculator. So minus 6.67 times 2.7 minus 4.45, and let's divide that by minus 6.67, and that's a positive quantity, 3.38. 3.38. All right, and obviously here we have to have a 0, but that's again, and s to the power 0, that's obviously going to be 1. Okay, so this is the entire constructed Routh table here for this. All right, so it's a pretty big one. Let's get rid of the calculator. Now you see, I mean, of course you understand how difficult it is to actually solve this polynomial, right? to actually solve this polynomial to find out the exact locations of the roots. And that is what I told you, right? So this is kind of a historical perspective, and back in the 80 years ago, people did not have computers, let alone calculators, right? People did not have these. The scientists working on these things did not have calculators, computers, right? And this kind of polynomials did appear for complicated systems like aviation, like airplanes, like any vehicles, any dynamic systems, very complicated dynamic systems. They often had to solve polynomials, or rather often had to figure out the pole locations for systems of order like 7, 8, 10, things like that. Okay, so the order of the system here is 7. Okay, it's a 7th order system because the order of the denominator's polynomial is 7. I mean, finding out all the 7 poles is very, very difficult, right? And of course, if one of them slightly changes, like this 3 becomes 3.2, then you have to solve it all again, right? So it becomes really difficult. Now you can see the amount of calculation that we have put in here is significantly smaller to the amount of calculation we would have put if we wanted to solve this polynomial and figure out all the exact locations of the poles, right? And of course, we had to employ something called Newton-Raphson method, okay, to actually figure this out numerically. But that is something we did not do. But in any case, we have put only a very small amount of effort here in constructing the Routh table. We know this satisfies the necessary condition, okay, but it does not satisfy the sufficient condition because we see that there is a sign change. You see, look through the first column of the Routh table. You see there are positive numbers, then we have a negative number, then we once again have positive numbers. So it is not satisfying the sufficient condition, and as such, this is not a stable system. This is not a stable system. But we can not only just figure that out, we can also figure out how many poles are on the right half plane. Okay, so it's a positive to positive transition, positive to positive transition, positive to positive transition, positive to positive transition. Then we have a positive to negative transition. So we can say this is a sign change, right? This was plus and then it became minus. So it's a sign change. There is another sign change. Okay, and then we have no sign changes. So there are 2 sign changes altogether here in this one as well. So there are 2 sign changes. Okay, 2 sign changes. So which means there are 2 poles in the right half plane. That is 2 poles are in the right half plane. So this polynomial is not a Hurwitz polynomial, okay, because it does not have all of its roots in the right half plane. 2 of its roots are on the right half plane, okay, and the remaining 5, because it has 7 roots, right? The remaining 5 are on the left half plane. Therefore, the system is unstable. System is unstable because 2 of its poles are on the right half plane and the remaining 7 minus 2, that is 5 poles, are on the left half plane. And as you know, it does not matter how many poles are on the left half plane, okay, as long as at least one of the poles are on the right half plane, the story is over, the system is unstable. So that is the example that I'm going to leave this class with. And there are a few edge cases. Edge cases are special cases. That is something we're going to discuss in the next one. Okay, special cases we're going to discuss in the next one. But that is the discussion as far as today's class goes. So if you have any query, feel free to ask at this moment. Otherwise, we are going to end today's discussion. All right. So please ask if you have any queries. So I believe you understood the difference between necessary and sufficient conditions. Okay. All right. So thank you very much for confirming, and we'll see you on Wednesday then.